Okay, good evening, everyone. Welcome to O-Level Physics lesson. Today, our lesson is on the last topic of physics, electromagnetic induction. Okay, my name is Mr. Chu. Today is Tuesday, 23rd August, 2022. Okay. As always, I'll always show you the topics of the whole of physics for O-Level. Okay, so now we are at the very last topic, electromagnetic induction. Okay, so the topic before this, we are talking about when there is a current in a magnetic field, it will produce a force. Okay, electromagnetism means when there is a current in a magnetic field, it will produce a force. Okay, so what is electromagnetic induction? It's the opposite. Okay, so with a force in a magnetic field, it will produce current. Okay, so electromagnetic induction is the opposite of electromagnetism. So when there is a force in a magnetic field, it will produce a current. Okay, that is how electricity is generated and why this topic is very important. Okay, so let's continue. Okay, not this one. Okay. Electromagnetic induction itself, there are four subtopics. Okay, there's a principle of electromagnetic induction, the AC generator, how to use a cathode ray oscilloscope, as well as the transformer. Okay, so all of you are required to know these four parts. Okay, so first of all, you need to actually deduce, okay, from Faraday's experiment on electromagnetic induction. So basically, when there's a changing magnetic field, it can produce a EMF in a current. Okay, that is how electricity is produced. Okay, the direction of the induced EMF oppose the change producing it, and the factors affecting the magnitude of the induced EMF. Okay, you need to know the factors. Number two, describe a simple form of AC generator and the use of slip ring when needed. Okay, number three, sketch a graph of voltage output against time for a simple AC generator. D, describe the use of a cathode ray oscilloscope to display waveform and to measure the PD and short interval of time. Okay, so basically you need to know how to use the CRO. And after that, you need to also know how a transformer, okay, why do we need transformer and how a transformer is used. Okay, so these are the outcomes that all of you need to know. Okay, let's continue. Okay, electromagnetic induction. Okay, electromagnetic induction is a process through which an induced EMF is produced. So basically, electricity is produced, okay, when there is a changing magnetic field. Okay, so Faraday law of electromagnetic induction says that the magnitude of this induced EMF is directly proportional to the rate of change of magnetic flux in the circuit. Okay, then Lenz's law states that the direction of the induced EMF and the induced current in a closed circuit is always such that the magnetic effect opposes the motion or change producing it. Okay, sounds very complicated, right? Okay, first of all, electromagnetic induction. The first point, if you understand, give me a yes reaction. Do you understand what this means? Give me a yes reaction. Okay, how about the Faraday's laws of electromagnetic induction? Do you understand this? Okay, let me just go on first. So basically, what is this? What's happening is this. Okay, we talk about the first one first. When a magnet is pushed into a solenoid, there is a change in magnetic flux cutting the coil. Hence, there is an induced current in the coil. Okay, when a magnet is pushed into the right side of the solenoid with the north pole first, okay, the right side of the solenoid becomes the north pole. Okay, when the magnet leaves the solenoid through the same side, the right side of the solenoid becomes the south pole. Hence, an alternating current is produced. The magnitude of the, okay, so basically what's happening is this. Remember I told you about this question. How do we actually create a current? Okay, how do we actually create a current? First, when there's a motion, okay, and a magnetic field, okay, you'll create a current. Okay, so in the previous topic, we used Faraday left-hand rule. Okay, so in this case, we actually use the right hand. Okay, right hand. Where there's a motion, there's a magnetic field, and there's a current. So we instead of left hand, use the right hand, and we do the same thing. Okay, the thumb is the force, the index finger is the magnetic field, and the middle finger is the current. Okay, where did Ryan go? Oh, Ryan changed the connection. Okay, so basically it's exactly the same as the previous topic, but instead of the left hand, we use the right hand. Instead of finding the motion, now you are using the motion to find the direction of the current. Is that clear? Okay, so basically, how can we increase the induced EMF? Okay, how do we increase the power of the current? Okay, so it's very, very simple. And these are things that you learned in electromagnetism before. How to create? How do you create a stronger electromagnet? Okay, same thing. Either you use the stronger magnet, or you increase the number of turns of the solenoid. Okay, and lastly, okay, you can actually increase the speed of the magnet that move with respect to the solenoid. So basically, when you do all these kind of these are the three factors that can actually increase the magnitude or the power of the induced EMF. And the induced EMF, okay, will actually produce the current. Okay, you'll hold for a while. Okay, so what is an alternating current generator? Okay, you'll pause for a while. Okay, so how do we use this theory to produce electricity? Okay, so for this topic, when we do the reverse, okay, when we do the reverse, we are talking about alternating current generator. Okay, for this theory, when we reverse the electromagnetism method, okay, we'll be producing an AC current. Okay, AC current, not a DC current. Is that clear? Okay, so how does this work? Okay, so a bit different. So can you see over here? in this case, when you turn the handle, you are actually giving a force. Okay, you're giving a force. So basically, like for example, when you turn clockwise, it is from this angle, BC will be going downwards, and then AD is going upwards. So there's a force, there's a magnetism, then electricity current will be produced. Is that clear about this? So let me go through the steps one by one and explain to you all. Okay, Ryan actually mentioned a question just now about when the North Pole. Okay, that one we'll go through questions next week. Then it will be clearer. Okay, let me go through this AC generator first. Okay, first of all, can you see in this diagram, this coil over here is connected to this handle. Okay, so when you turn the handle, we turn it clockwise. At BC, the force is going down. At AD, the force is going up. Okay, as the coil rotates in the magnetic field. Okay, so what happens is this: as you turn this thing around, BC will be going down, AD will be going up. So all of you take out your right hand. Okay, remember the 3-letter FMC. You remember FMC stands for what, right? Okay, so the force, okay, we talk about BC first, BC. When the force is going down, the magnetism is going from left to right. Your current will be moving from C to B. Okay, your current will be moving from C to B. Is that clear? Okay, so the current will be going from C to B. Okay, so AD, same thing. Okay, so if AD, the force is going up. So take out your right hand, your thumb pointing up, your index finger move from left to right, and then your middle finger be pointing from A to D. Is that clear? Okay, so this is what happened. So the current will be moving in this direction. Okay, in this direction from C to B as well as A to D. That's how the current will move when on the right side is like this, on the left side is like this. So as the coil rotates in the magnetic field, okay, as the coil rotates in the magnetic field, the change in magnetic flux creates an induced EMF. Okay, why is there a change in magnetic flux? Okay, because as the coil is moving downwards, the magnetic field is a bit different, correct? So there's a change in the magnetic field while you're moving. So this change in the magnetic flux creates an induced EMF. Okay, it creates an induced EMF that creates an induced current. So in this case, from what I explained, the current will move from this way to this way. So now in the third picture here, what happened is that the whole thing turns. It turns 180 degrees. So now AD at first is moving from A to D. As it turns to the other side, it's moving from D to A. Can you see that? So basically this picture is number 3. Can you see this picture number 3? This picture is number 1. Okay, so what happened is this. So we talk about let me see, this one EMF V. Let me see. Okay, so in this case, we talk about, let's say, which side? We talk about, let's say, AD. Okay, when AD is moving from A to D, it is positive. Then it's moving from D to A, it becomes negative. So as it's going up, the perpendicular distance is lesser. Do you remember last week? When the perpendicular distance is lesser, the moment is lesser, correct? So with a lesser force, if a same magnetic field, your force will go down. When it becomes vertical, okay, when it becomes vertical, the two sides actually cancel out each other. Okay, so when it is on this side, the two sides actually cancel each other. Can you see the force? The force as C is to the right. The magnetic field is the same direction. So when the magnetic field and the current and the force is in the same direction, there will be no induced EMF. There must be certain direction, certain angle between the magnetic field and the force to produce, okay, to produce a current. Is that clear? Okay, so number five. Okay, we back to AD. So 1 and 5 are the same. When you back to AD, okay, you have a maximum force. Okay, why did I change thing here? Okay, so it is at the furthest perpendicular distance, so therefore the force is the greatest. So when the force is the greatest, you'll give a greatest EMF. Clear so far? Okay, so let's go to number 4. Okay, so basically I've talked about 1, 2, and 3. Are you all clear about 1, 2, and 3? Okay, we are clear about 1, 2, and 3. So let me go to number 4. Okay, now in the previous topic, what we have is not a slip ring. You get a split ring communicator. Okay, so that in one side is always the same direction. Okay, in one side is always the same direction. So the slip ring are always in contact with the carbon brushes. So there's nothing to split because you want the current to change every 180 degrees. Okay, so this ensures that the induced current is always transferred to the external circuit. Okay, it's always transferred to the external circuit. And then the induced current will power the electrical load connected to the external circuit, so the LED will light up. Okay, so for this whole idea, okay, basically there's only three changes. Compared to a motor. Okay, for a motor, just remember, motor, you are using current to produce, okay, current in a magnetic field to produce force. Okay, in a generator, you are using a force in a magnetic field to generate electricity. First difference. Number 2, in the motor, you use Fleming left-hand rule. Okay, but you still use the same FMC, the same fingers for FMC. But in an AC generator, you use, instead of left hand, you use right hand. But likewise, your thumb is still the force, your index finger is still the magnetic field, and your middle finger is still the current. So that is the second difference. And then what's the third difference? The third difference is that in a AC generator, okay, you are using a continuous slip ring. Okay, you're using a continuous slip ring, whereas in a motor, you are using a split ring commutator. Is that clear? Okay, last thing that I forgot to mention. The fourth difference is that in a motor, you use a DC current to generate motion. Okay, for an AC generator, you are using motion to generate a AC current. Okay, do you all know why it's AC and it doesn't produce DC? You all know about this? Okay, so now there's another fighting here. Okay, so let me read the fighting below. Okay, so you read the fightings below. Let me go through this with you. Let me clear this up. Okay, so when the plane of the coil is parallel to the magnetic field, so when it's parallel to magnetic field, it's moving up, right? As it turns 90 degrees, moving to the right. So when it's moving up, there's still an angle between the force and the magnetic field. The magnetic field is left to right. Okay, there's still a force, in this case 90 degrees. Okay, when there is an angle, then you produce electricity. Okay, you produce electricity. Okay, number two, you look at number two. If in this case, can you see, because you have turned 90 degrees, the force now is left to right, and there's no more angle between the force and the magnetic field, so therefore there'll be no induced current. So you see zero, no EMF here. Okay, so let's go through number one. When the plane of the coil is parallel to the magnetic field, basically the force is perpendicular to the magnetic field. Okay, there will be induced EMF, so the current will be the greatest. Then when number two, when it is now perpendicular, when the plane, talking about plane, when the plane is perpendicular to the field, but I don't like talking about plane. I talk about AD. When AD, when the force, right, the force of AD, which is this one, when this force, when the force is parallel to the magnetic field, okay, when the force is parallel to the magnetic field, okay, then it does not cut through the magnetic field line anymore. Okay, so the rate of change of the magnetic flux is zero. So the magnetic of the induced EMF will be zero. Okay, so the rest are not mentioned anymore. So are you clear about the concept? You look at your hand, whether is it left hand or right hand. When you point out your thumb and your two fingers, they are all 90 degrees to each other. Okay, in O level, we talk about 90 degrees. In real life, the thing can be at a smaller degree. Basically, when two of them are not parallel, you produce a third component. Okay, but for easy sake, in O level, your thing have to actually, okay, your okay, for easy sake, it's O level. We just talk about there are the three forces, okay, not forces, the three components, the magnetic field, the current, and the force are all perpendicular to each other. Okay, so that is what you need to know in O level. Okay, so for now, I know this is very, very complicated. I mentioned the four differences. Okay, are you clear about this? Can everybody remove your yes reaction for now? If you understand very well alternating current generator, give me a clap. Okay, if you understand very well, give me a clap. Okay, are you all very clear about this? Because when the first time I learned about this, I get very confused. Okay, Yu Ting asked me a question. What is a magnetic flux? Okay, what is a magnetic flux? Hao Rui asked me another question. Okay, can Yu Ting and Hao Rui share your question to everybody? Okay, Yu Ting, you mentioned about what is a magnetic flux. Okay, so if I were to put a piece of, okay, let's say number two, we talk about number two, okay? Number two, okay, let's the dotted line be the magnetic field line. Can? And I let number two be a piece of paper. Okay, a piece of paper. Okay, this one is actually not very important for this. Okay, so magnetic flux is this plane. that is perpendicular to the magnetic. Okay, it's perpendicular to the magnetic field. Okay, so it's this plane, this surface that is perpendicular to the magnetic field, and how many magnetic field that actually cut through it. Okay, in O level, you don't need to define what is a magnetic flux. Okay, basically it's something like magnetic field, but in this case, it is not a magnetic field, but it's just a surface. Okay, it's just a surface that is 90 degrees to the magnetic field. Okay, and you are supposed to determine how much. Okay, it actually is a measure of the total magnetic field that pass through this surface. Okay, actually it's actually the measurement is a measure of the total amount of magnetic field that pass through this given surface. Okay, so for O level, there's no such need to actually understand or to memorize what is a magnetic flux. Okay, but magnetic field you need to know. Okay, magnetic field is a region okay, where a pole of a magnet undergo a magnetic force. That one you need to know. Okay, a magnetic flux is basically a surface that is perpendicular to the magnetic field, and it's a measurement of how much magnetic field pass through this plane or this surface. So of course, when there's a lot of magnetic field passing through it, then the magnetic flux is stronger. Is that clear? There's a formula for this. You'll learn that only in A level. Yeah, because right now everything is 90 degrees, there's no need to learn so much. So in A level and beyond, this plane might not be 90 degrees to the magnetic field. Okay, so there is an angle. So when the angle is 90 degrees, when this is 90 degrees, you have the maximum value. Okay, so maximum is actually 1, which is cosine cosine 0. Okay, is that correct? Cosine 0. Then the minimum is actually 0, which is cosine 90 degrees. So in this case, this field, okay, sorry. Okay, basically what I'm trying to tell you is this formula, there's no need to know, but how the value actually vary depends on your cosine angle. Okay, when it's maximum at 0 degree, in this case, when it's maximum at 0 degree, you have the maximum magnetic field. When it's at 90 degree, when it falls down to like this, you get, sorry. I am sorry, yeah. This one over here. Can you see here? Okay, so in this case, okay, so what I'm trying to say is that different angle give you a different value, and it's determined by your sine graph. So can you see this sine graph? When it's maximum, it's like this. When it's minimum, it will be at 0. So it'll be going up and down, up and down. So what's the difference in between depends on the cosine of the angle. Is that clear about this? And that is, you do not need to know at O level. You only need to calculate that in A level. Okay, next question by Faraday is, does the slit ring also prevent the wire from entangling? Okay, the slit ring makes sure that the current in BC on the BC always goes to one of the wire, and then the AD will always go to the other wire. So it will continuously be connecting to the same wire. Okay, the previous topic we talked about split ring commutator is to make sure that every time there's a 180-degree turn, the wire change direction. Okay, the current change direction. Okay, so therefore in this case you cannot use a split ring because you don't want it to change direction. So you just use a continuous ring, a ring that's not split. Is that clear? Faraday, both the slit ring and the split ring commutator ensure that the wire don't entangle. Just therefore, slit ring is continuous. for split ring, it allows the wire to actually change direction. Is that clear? Okay. So the factors of the how strong or the factors that affect the magnitude of the induced EMF or the current depends on a few things. Okay, same thing as just now. You use a stronger magnet, number one. The coil, what you see here is a single coil. If this coil is a lot of coil, if you increase the coil, the induced EMF will be greater as well. Then if you turn the coil faster, okay, if you turn the coil faster, it will also increase the induced current. Lastly, winding the coil around the soft iron core. Okay, you put a soft iron core inside this coil. Okay, you put a soft iron core inside this coil. You also improve. Okay, you also actually strengthen the magnetic flux linking in the coil and therefore increase the magnitude of the induced EMF. Is that clear? Okay, so these are the factors that affects the magnitude of the current. Okay, so what else is there? Increasing number of turns per unit length also increase this. So basically what is written here, okay, emphasize on these 4 points. Okay, this one I think you all don't need to memorize by doing a few questions. You all should know what are the factors that can increase your electromagnetism. Am I right? Okay, so this one. So what is the application of this? Because you're trying to produce electricity. Okay, so a generator generate electricity. So what happened in this case is this. This is another example, slightly different. Instead of turning the coil, you turn the magnet. Okay, you turn the magnet instead, rather than turn the coil. So when you turn the magnet, okay, the magnetic field will keep on changing. So when you keep on changing, you induce EMF in your copper coil, and therefore current will be produced, and therefore you light up the bicycle light. So this is another example which you turn the magnet and not the coil. In this case, you turn the coil, the magnet is stationary. In this example, you turn the magnet, okay, and then the current is actually produced in the same way. Is that clear so far? Okay, anybody have any more questions? Do ask me in the next 30 seconds. Okay, so the last part of this topic before I go to CRO is a very interesting application that allows electricity that comes to our house. Okay, so what is this? Okay, we're talking about a transformer. Okay, basically a transformer is transferring your electrical power from a primary side, okay, a primary side to a secondary side. I repeat myself again. A transformer actually allow you to transfer the electrical power from one side to the other side. Okay, why do we need to do that? Why don't we just connect why don't we just do this? Like this. I have a VP here. Let's connect all the way to the load lah. Why do I need to go and have this thing in the middle? Why can't I just at the generator, a power plant? I just connect one wire, no, the live wire all the way to your house, and then the other neutral wire to your house. Why can't we do that? Why do we need to have this kind of thing that complicate the whole circuit? Okay, so over a very long distance, okay, over a very, very long distance, okay, over a very long distance, electricity will lose its energy, okay, over long distance, especially if you have a very high current. I repeat myself again. In your current is very high, you will lose you actually lose your electricity energy. So power plant are usually not beside your house. It could be many kilometers away. And when you want to transmit power to your house, okay, at 230 volt, which is what our house uses, your current will be very high. And as the current is very high, you will lose your energy very quickly. Okay, so what you need to do is you need to step up your voltage. Okay, you need to step up your voltage so that your current will be very, very low, and therefore you will lose less power. Okay, lose less power. Okay, so what do we, okay, let me talk about this. Okay, so how does this work? Okay, how does this work? Let me show you. Okay, so let's look at this. So we have a coil A and a coil B. Okay, a coil A and coil B. Let me read the thing here. Okay, so what I mentioned just now is the last point. When we want to transmit or transfer electrical energy, we use transformer to step up the voltage. Okay, why? You remember the formula of power? Power is VI. Okay, power is VI. So when we increase the voltage, we maintain the same power. Power is produced by the generator or the power plant. When we increase the voltage, if we can increase the voltage, our current will be very low. Okay, given the same power, if we can step up the voltage, the subsequent current will be very low. So to make the current very, very, very small, so therefore your electrical loss will be low. Is that clear? Okay, so I use the formula P equal to VI. So when our V is very high, our I will be very low. Okay, our I is very low. So therefore, when with a low current, we actually have a lower power loss. Okay, so in the formula here, it's the same thing. Okay, you also get IR squared. So when your current is very low, the resistance is the same because the wire is the same distance. The wire can't become greater or lesser. Yes, you can still control, but there still be some resistance in your wire. But when your current is very low, your power loss will be lower. Is that clear? Your power loss will be lower. Can? Okay, so how does this whole thing work? Okay, how does this whole thing work? Basically, how the voltage step up or step down is based on the same ratio as the number of coil in your left and right. You understand what I'm trying to say? Okay, so if the number of coin on the left is 2 times is to 1. Okay, so the voltage, okay, the EMF also will be in the ratio of 2 is to 1. Is that clear? Is that clear? Okay, so what you do is the thing that correspond. Okay, we talk about when we talk about transformer, we talk about step up and step down. And what are we stepping up and what are we stepping down? We are stepping up and stepping down the voltage, the EMF. Is that clear? Okay, so the coin, the number of coins difference between the left and right side is also based on the ratio. Okay, so if there's more coin on the left, your EMF is higher on the left. If there's less coin on the right, there'll be less EMF on the right. Is that clear? Okay, so for transformer, can you tell me why do we use a transformer? Can you tell me the reason why we use a transformer? Or type out the reason why do we use a transformer? Why do we learn this complicated thing? Why don't we just connect the battery all the way to the compass? Why don't we just do that? Okay, waiting for your answer. Why do we learn transformer? Okay, Yuting mentioned to reduce power loss. Okay, very good. Why do you want to reduce power loss? Because you need to reduce the current to become very small so that there will be lesser power loss. Can? Okay, so the last part for today will be on cathode ray oscilloscope. Very hard to discuss about this unless we do questions. Okay, so can you see over here? Are you familiar with handling cathode ray oscilloscope in your school lab? So Pei Kwan say no, Yiting say never. How about, have you all seen teacher demonstrating the CRO in front of you? Also don't have. Okay. All right. For cathode ray oscilloscope, okay, let me just explain a bit. The picture, let me see. I also hardly used it last time when I was a teacher. Okay, so basically, there's this thing called X shift. Let me see. Can you all see the word here properly? Okay. Okay, basically X shift is okay when you actually display wave, and when the wave doesn't move anymore, means that it's always moving from left to right in this same journey. X shift is just shifting your waveform to the left and right. That's all. Okay, Y shift is to shift it up and down. Okay, Y shift is to shift it up and down. Okay, so what is a Y gain and a time base? Y gain is basically changing the magnitude of your Y axis. So Y axis is like your the car, in this case could be current. So you just want to change the magnification of your current. So if your wave is very, very small, you want to increase the magnification, you change your Y gain. Okay, same thing for time base. Okay, sometimes you may see the wave very close together. You want to see the detail and spread it out. So you actually adjust the time base to actually widen the wave, or you squeeze the wave further. Okay, that is what the time base is about. Is that clear? So how to actually use this thing? So you plug in your, okay, there are two waves you can actually observe on the left and on the right. So basically you bring your signal, you plug into your channel 1. In this case, channel 1, and here is your channel 2. So ignore channel 2, I talk about channel 1. Okay, talk about channel 1. Okay, so how do you actually play with this? Okay, so from here, can you see? This is like your positioning when you move the thing up and down. Okay, and this is your gain. Okay, your Y gain, where you change your magnitude become greater or lesser. Okay, likewise for this one over here is your time base. Okay, sorry, not time base. This is actually your shifting your signal left to right. Okay, this thing itself is to shift your signal left to right, and then your time base, if I'm not wrong, is here. Can you see this? This is your time base. Clear so far? So you actually adjust left to right. Okay, so this time base actually make your graph. It actually change. It doesn't change your frequency, but it change the display, your scale of your time axis to become squeezed more together, or actually lengthen it together. Is that clear? So this is how CRO work. We'll go through some question, and then we will see how to adjust this thing in the O-level question. Okay, so for this topic, we have roughly clear this thing. I know that it's not very easy, this topic. Transformer, are you okay about this? Are you okay about transformer? If you're okay about transformer, give me a yes reaction. Okay, one more thing I did not mention about transformer is that even though we have transformer, it is still not 100% efficient. 100% efficient means what? Okay, 100% efficient means before it gives you 100 watt, after it still gives you 100 watt. Okay, a transformer is still not 100% efficient. Okay, there will be some loss of power. Okay, even when you use a transformer. Okay, so the efficiency of a transformer is measured by the output power. So on the right side here is your output. Your left side here is your input. And input, we usually call it the primary. and the output we actually call it the secondary. Okay, are you all clear about this? Okay, so to measure the efficiency, okay, so you just need to measure the V secondary and the I secondary over the V primary and the I primary times 100%. Okay, you will get the efficiency of the transformer. Is that clear? Okay, so why in this case, okay, so are you clear about this? How a transformer work? So a transformer try to transmit power from the primary to the secondary coil. Okay, so on the secondary side, there's no battery, right? But you can see that there'll be current over here. So quite amazing, huh? And you use a transformer to step up and step down. Okay, so let me just go through one last thing. So basically in a power plant, okay, it will go into before it transmit, you will need to have a step up transformer. Okay, then you will go to the super long wire. Then you'll bring to the step down transformer. Then you go to your houses. Okay, so in a power plant, when you produce electricity, okay, before it transmit long distance to your house, there'll be a step up transformer. Then there's a step down transformer. Then you go to your house. Is that clear? Any question for me? Okay, so this is the example of a transformer. Okay, your current is AC current. So the number of coil, okay, the number of coil, NP is NS. The ratio is the same as the voltage of the primary and the voltage of the secondary. So what so these two are the same. So when you have more coil on the secondary, your voltage will be higher on the secondary. Okay, is that clear about this? Okay. Do you all have any question? I think the thing is about the going through question, you will actually understand a bit better. Okay, so this one, I think you all understand already. Transformer. Okay, basically the two main things you all need to understand is how a AC generator work, as well as how a transformer work. Is that clear? All right. Okay, if there's nothing else for me, today we end a bit earlier. Then next week we go through question. Okay, so can you all give me two things that you learned today? Once I call your name, you may leave the class. Okay, Yu Ting says that P equal to I square R tells us how power is lost. Okay, so this shows this formula shows that when the resistance is the same and the current is very high, you will lose a lot of power. Okay, Yu Ting, you may go. Okay. Ryan says since V is low, I is high. Why? Because when power is the same, when power is the same, and V is inversely proportional to current. Okay, that's the reason. Okay, when power is the same, V is inversely proportional to the current. One more thing, Ryan. Ryan says that the formula is not for this topic lah. Something that you learn about this topic. A light pole is induced when a magnet is brought near a coil circuit. Okay, what else? This topic is for the no, it's for the practical electricity topic, not for this topic. What else do you learn today? Okay, Beikwan, you learn magnetic flux and understanding transformer. Okay, you may go. Okay, thank you everybody. Have a lovely evening.